Welcome to Seeing More of the Universe. I'm your host, Alyssa Goodman. In this episode, we featured this funny looking cube to remind us of a very important concept that I like to call data dimensions display. What does that mean? What it means is that when you look at any particular display of data or when you consider any particular data set, you want to think about what the intrinsic number of dimensions of the data that you have are and what the number of dimensions of the display you might use are, and how to match together these different properties. And so, what I mean by dimensions is not necessarily spatial dimensions. It's kind of how many columns of information do you want to display at once, if you think of it as a table. And so, a simple graph is a two-dimensional display. This one is meant to represent something on a piece of paper. And you could think of the number of dimensions displayed as either one, whatever is on the y-axis is the function of some index on the x-axis, or sometimes you could think of it as two if you want to think of the y and the x-axis as independent. That's not really important. What's important is that it's not hard to show one thing as a function of something else on a simple graph. Okay? But if you have three-dimensional information, you have some interesting choices on a two-dimensional display. And one is shown here, which is a series of stills. This is a familiar kind of image where you're looking at scans through someone's brain that I can make go faster and slower here with a slider. And if you know what somebody's brain looks like, that's a perfectly fine way to display three-dimensional information. But for structures like this one here, which is showing you the structure of a star-forming interstellar cloud, as I will show you later, if you do it a slice at a time, it's very hard to reconstruct a three-dimensional view. A really great option that people usually don't think about is building an actual three-dimensional model. This one shows the structure in three dimensions of the Orion area of the sky and was made using craft supplies by a group of world experts on Orion who were lucky enough to be in the same room. Admittedly, this is a kind of niche use case, but don't forget the value of actually making things in three dimensions. With today's technology, there are options for making things in three dimensions that use augmented reality, which you see here on a two-dimensional iPhone screen, but you're displaying three-dimensional data and you have the option of making the data float in space and being able to walk around it. So just how many dimensions that is something you could argue about. But what's important here is that in creating all of these displays, people have thought about carefully the number of dimensions they want to display and what it is that's available on the display that they have at hand. So what I want to do next is talk about a little bit of a formalism to let you think about data as being part of a high dimensional space. So if you take a look at this cube and just pretend that it's any three columns in a table, and in an astronomy example, you could pretend that two of those columns were, say, dimensions or coordinates on the sky, and one of them was intensity of something, and another column was, say, frequency or wavelength, and that would be a spectral line data cube. And some sort of cut through that in just one dimension then could be a graph, and that graph could, for example, again, in astronomy, be a spectrum, if this was what astronomers would call a spectral line data cube. But remember that this can be any arbitrary space. And so here, now, if I cut in two dimensions, I can either think about a face of this cube where you sum through it, or where you slice, like we saw in the brain imaging example, and you would get an image that is a slice of this cube that you would want to display typically in two dimensions. Now, if you think about the whole cube as a three-dimensional volume, you start running out of dimensions on a screen, and so you have choices like the three-dimensional rendering we saw before or the two-dimensional series of slices we saw before to represent 3D data. And then if you have three-dimensional data that changes with time, so like some kind of time series of volumes, then you pretty much have to go to some kind of moving display, like some kind of movie of a three-dimensional object changing in time. Because these concepts are somewhat abstract for someone who's seeing them for the first time, I'm going to return to them later with concrete examples, and I'm going to use these little icons to remind us of 1D, 2D, and 3D views of high dimensional data. So just keep those in mind. One interesting quantity that people can think of as a dimension in astronomy is actually wavelength itself. And this view that you see here is a screenshot from a program called Worldwide Telescope. And what we're going to do is we're going to use it in a minute to see the sky at different wavelengths and try to think about how those represent different dimensions. But I just want to point out that the kinds of concepts I'm talking about now are discussed in more detail in the 10 questions to ask when creating a visualization website itself and on the video that is specifically about that website. So please take a look at that. For the moment, though, let's think here about this region on the sky, and we'll start with a simple optical image, okay? But then we'll take that optical image and we'll contextualize it using Worldwide Telescope. And in Worldwide Telescope, I can choose from many different all-sky images at different wavelengths, and I can show sort of compared to what concept that you'll see in the Tufte video. Here you can see the optical historical image compared to relatively modern all-sky infrared images of the sky. And so those are really two different dimensions of data. You can also get a lot more information about that particular place on the sky using Worldwide Telescope. And you could think of that deeper information that you get in something called the finder scope as metadata attached to the position that you see on that two-dimensional display. But again, please take a look at the 10QViz video to learn more about metadata. For now, let's think again about wavelength as a dimension. So we saw just two wavelengths, optical and infrared, a moment ago. But in fact, people can create what's called spectral line data cubes, where you have many wavelengths closely spaced together, and they can be used to measure the velocity of gas in radio telescope observations. And so that was what was done more than a decade ago now using something called the Complete Survey of Star-Forming Regions. And this display that you see here is actually a compilation of many different kinds of data that are themselves quite high dimensional in that they are taken at different wavelengths. But one of the data sets, the one that's marked with green contours here, is itself actually three-dimensional. And we'll return to that in a moment. But I just first want to do a little advertisement for our next video that's about the differences between wide data and big data, and point out that the many layers of information you see here, and it doesn't matter what they are for the moment, but you can look at the key, represent wide data. And the discovery power here is actually both from combining many different data sets to investigate this region all at once, and from the high dimensionality of the particular data set I'm about to talk about. Okay, so if you take a look at those green contours, it's kind of a travesty to see the data this way, because the truth is that those green contours are the sum of many quote unquote channels of information that you see. If I slide through the data cube here, the sum of all that white fluff is the green contours. And what I'm doing here is the equivalent of sliding back and forth through somebody's brain scan, showing you different layers of the cube, different slices as I slide. And again, if this was a brain scan, you would be able to put that image back together in three dimensions in your head because you're an expert radiologist. But as no one had ever seen the Perseus star-forming region in what's called position-position velocity space, this abstract pseudo 3D space, before, it was really hard for anyone, including the experts who made that, to do that. So instead, you can put this into an actual 3D image and rotate it around to take advantage of perspective, shading, and occlusion, important cognitive concepts, to let people think that they're seeing a three-dimensional object on a two-dimensional screen. So just to review for a minute, we're talking about some data that has two dimensions on the sky and one dimension along the line of sight, but that is actually velocity. So while that looks like a real three-dimensional object, it actually isn't. As an aside for the astronomers, we can now actually measure the structure in three real spatial dimensions, but that's a subject for another day. Instead, let's consider all these different data sets and think about a decade ago how difficult it was to combine them all and how many graduate student hours that took. Today, it's much easier to do that. I'm really happy to say that there's a software program called Glue that we'll talk about in another video that makes combining different data sets and then combining different views of those data sets in ways that allow for exploratory data visualization and especially for the exploration of particularly salient features that one finds in that analysis, like what you see highlighted in yellow on the screen here, possible. Again, that's the subject of another video, though. And here, what we want to do is return to these concepts about data, dimensions, and display specifically, and think about the dimensionality of the different views that you see on the screen here now. If we start at the upper left, you're seeing something that's vaguely the equivalent of the green contours that you saw earlier, where you take a spectral line map that is inherently three-dimensional, but just look at it, two dimensions all projected onto the sky. In Glue, though, you can connect the missing dimension to another display. So let's take a look here. If I turn on this little tiny yellow probe in that upper left-hand plot, and I think about what would happen if I could go into the screen and see the spectral dimension that's being hidden in that two-dimensional display. I could see these spectra of the various different spectral line tracers that have been observed in that region. And so together, those are the three dimensions: spectra into the screen, and then intensity on the sky, either summed or as a function of depth into the screen. In the case that you see here on the upper left, they've been summed. But really, what do those data look like if you wanted to see them in a fully three-dimensional view? And please forgive me, this is a two-dimensional screen, but when I say three-dimensional view, I mean a kind of moving, lit, three-dimensional representation of the data on a two-dimensional screen. And so you see here someone rotating the data around, adding and subtracting axes so that you can have some context for what's going on and which dimension is which. And that person can actually use their own brain power that includes a cognitive system that uses perspective, shading, and occlusion to let you understand the nature of a three-dimensional object in a two-dimensional display. Now, of course, this is, as I said earlier, not three real spatial dimensions here. Those are the dimensions that are shown in the two upper left plots, the two on the sky and the one along the spectral axis, but shown as a three-dimensional display that lets a person get a visceral understanding for really what the features are within the data set. Now, to move to some of the other displays that are on the screen here now, take a look on the upper right, and you'll see just a regular two-dimensional graph. So that's a graph of the properties of the material that's being probed in the three-dimensional displays, where all mention of coordinates has been removed. This is just a 2D graph. In this particular case, it happens to be of temperature versus velocity at different positions, but again, the position is not shown directly. You notice that someone has highlighted a bunch of yellow points in that graph, again, using the linked view capabilities of Glue that we're going to discuss in another video. But you see those yellow points at the lower right are displayed in a different two-dimensional display that's essentially a map of the positions on the sky that go with what's in that graph. And those highlighted features can update live as somebody changes the highlighting. But what's important here is that you have different displays showing you different dimensions and you're connecting them for insight. And then if that wasn't enough dimensions, if say you wanted to see another property of the data at the same time, you could actually use a 3D point cloud that you see here in the middle on the right. And again, those yellow points are highlighted to connect the concept that the person is trying to explore about them being outliers in the upper right plot. So last but not least, let's take a look at this bottom middle panel, which actually comes from a plugin to Glue using the American Astronomical Society Worldwide Telescope program that I mentioned earlier. And what that lets you do is bring in even more data. So you see that the data that have been included here are already what we would call wide data, but we can make them even wider by bringing in other wavelengths online using Worldwide Telescope. And if you look really carefully, you'll see that those yellow points are actually even carried over to the Worldwide Telescope display. So this is a lot of data in a lot of dimensions using a lot of different kinds of display. And the last and perhaps most important point I want you to take away here is that what you see on the screen is about a particular spectral line data cube and a particular star forming region. But the kinds of displays you see here are really just images and graphs and 3D volumes and could be repurposed to all different kinds of data. And it's really just understanding how a particular investigation or a particular kind of data maps to this high dimensional thinking and the ways for displaying high dimensional data that's really important. I think I've said enough about data dimensions and display for now. But I'd like to remind you that I also said plenty about big and wide data and about linked views and exploratory data visualization. The next two videos, however, will focus on specifically the value of wide data and the value of linked views. So we hope you enjoy the entire series. Thanks again.